Okay, we are going to go through your next lab here. So, this is determination of Ksp for the solubility of KHTar as we get into this. But we got to outline our steps here of what the actual procedure is. So, I'm going to go through this. I would imagine, well, we have done Ksp already. So remember, in your Ksp, we do not include liquids or solids in any equilibrium. So we want to see how much of this potassium hydrogen tartrate, or better known as K for potassium tar. So how much of this is going to dissolve? That's how we calculate Ksp. You do know that. So this is what we're talking about. But we know that this potassium hydrogen tartrate, since this is a potassium compound, this is going to dissociate 100%. And when that dissociates 100%, you know for sure you're going to get K+, and you're going to get HC4H4O6- ion. Now, this HC4H4O6- ion, hydrogen tartrate ion, then has an ionizable hydrogen right here. So this is a weak acid. It has a Ka value. So what we're going to do, to summarize what we're going to do for this lab, is we are going to titrate this hydrogen tartrate ion with hydroxide, OH-, and we know for sure that this, the OH- is going to pull that hydrogen off as a 1-to-1 ratio and create water. And then the leftover, of course, is going to be C4H4O6, 2-. So if we titrate this with hydroxide, which is going to force the hydrogen off here from our tartrate ion, we can calculate what the molarity of this hydrogen tartrate ion is. And since this splits up 1-to-1, we're also going to know what that is. So let's go over the lab here a little bit. Again, we are going to calculate the solubility of potassium hydrogen tartrate. We know it's only slightly soluble in water. And this is actually cream of tartar. And cream of tartar is used in baking as an acidifier to release carbon dioxide from baking soda. And this is our structure. Again, this is going to split up. This 100% dissociate. We know that this is going to split up into these ions. Okay, so let's go to the next page. So this is the shorthand way to do potassium hydrogen tartrate. Again, however, this shows a solid. So in this case, the way this equation looks is we have an equilibrium set up because we are going to make a saturated solution in which the potassium hydrogen tartrate will be sitting on the bottom as a solid, and then we know that we are going to get potassium ions and what dissolves as H-tar minus in solution. Okay, oops. Now, so this is our potassium hydrogen tartrate. We are going to make sure that we have a saturated solution by stirring this for at least 5 minutes, and then we're going to filter it out. So our dissolved ions are going to go through the filter paper, obviously. Then this would be our Ksp expression. Okay, we know that Ksp is a solubility product constant, product multiplication, right? So Ksp is fixed at a certain temperature. Then again, we are going to titrate this hydrogen tartrate ion, which is a weak acid, with hydroxide, and that hydroxide is going to come in from sodium hydroxide solution, where sodium will be a spectator in this, but this hydroxide here will force the hydrogen off. We are going to get water and the tartrate 2- ion. Since this is a 1-to-1 reaction, the number of moles of hydrogen tartrate here is equal to the moles of OH-. So that's the key to it. Then, of course, we can get our Ksp out of this. We also know that our K plus is equal to our hydrogen tartrate ion. So really, once we know this from our titration, we know that as long as there's not another spectator ion in there, which we are going to explore, these two should equal to each other. And once we know this, since these are equal, we should be able to square it to get our Ksp value. So here, again, I said that this hydrogen tartrate is a weak ion. It has a Ka2. Well, you might ask, why is it a Ka2? Because tartaric acid is H2C4O6, which is also a weak acid. So it has a Ka1 of 9.2 times 10⁻⁴. And then once the first hydrogen comes off, then we have this hydrogen tartrate ion, which has a Ka2. That would be a diprotic acid, 2 ionizable hydrogen that can come off. Okay, so we are going to explore in this lab, though, the common ion effect. And that is going to be the potassium ion. So here we have potassium because the compound is potassium hydrogen tartrate, but we are going to dissolve that into a potassium chloride solution that is going to have some extra potassium in it. All right, let's go to page 3. So we are going to investigate the answer to that question is, how is the solubility going to be affected when we have a common ion in there? So, should we expect the solubility to be higher or lower than in pure water? And the value of the solubility product constant remains constant. Okay, there's a Ksp, it is a constant. And again, that depends upon the temperature. So let's go down here. We've got to talk a little bit about ion strength. So, we know that potassium hydrogen tartrate ions, the presence of positive and negative ions around these ions in solution inhibit their movement, impacting their effective concentration. Solutions containing common ions will certainly impact the solubility. We know that. But the presence of so-called inert ions, which do not appear in the equilibrium expression, will alter the solubility as well. So again, we're studying this Ksp. But how are, first of all, common ion, K plus, going to be affected? In order to keep our ion strength constant to compare this, we are going to dissolve potassium hydrogen tartrate in deionized water. We're going to do it. We're going to dissolve it in a solution that contains the common ion, potassium chloride, and then we're going to make sure that we have a control group. This sodium chloride does not have a potassium, does not have a common ion. So we kind of keep the chloride inert ions constant. And just to make sure that we are keying in on the common ion effect of potassium. And you could say, well, we're keeping the chloride ion constant, would be another way to look at that. So let's go to page 4. Nope, page 4 is our pre-lab. We're going to skip that. Let's go to page 5. Okay? So here's what we need to do, and I'm going to play a YouTube video within my YouTube video. Let's see if I can get rid of this off the screen. There we go. Well, sort of. Okay. So here are our 3 solutions that we are going to make. Beaker number 1, we are going to have potassium hydrogen tartrate in deionized water. Okay, so I'm letting the potassium be red in this case, and my hydrogen tartrate green, plus and minus ions. Again, this is saturated solution. All of these, there's nothing on the bottom, so these have already been filtered. So we are going to do potassium hydrogen tartrate and filter it in water. Then we're going to dissolve it in 0.1 molarity potassium chloride. This is our common ion. So if I say this is my original potassium and my hydrogen tartrate that dissolved, I also have Cl minus in there, and I have my common ion there. And in the third kind of controlled beaker, I have potassium and hydrogen tartrate that dissolves, but in order to keep those inert ions the same, I also have sodium and chloride, kind of as a control group. Okay, and then we are going to titrate them with sodium hydroxide. We know that the hydroxide ion is going to pull the hydrogen off in each case, right? So we know that however much hydroxide ion we use, that is going to equal this concentration, this concentration, this concentration. And by that, it's the hydrogen tartrate ion concentration. So I'm going to pull up a YouTube video at this point. So I have a YouTube video with my YouTube video. And we are going to look at that. If I bring this over to my other screen, I think.
Chemical equilibrium 2, the solubility product. The solubility product of potassium hydrogen tartrate.
It's not letting me go there. For some reason, it has that locked out. So I am going to...
Is measured out, and the effect of a common ion on its solubility is examined.
I am going to have to do this. Let's see if I can get it on this screen. There we go. Sorry about that.
Chemical equilibrium 2, the solubility product. The solubility product of potassium hydrogen tartrate is measured out, and the effect of a common ion on its solubility is examined. Transfer some of the sodium hydroxide from the main source into a clean, dry, medium-sized beaker.
Our sodium hydroxide is going to be 0.0500 molarity.
Record the concentration of the sodium hydroxide solution. Prepare the burette as demonstrated in another video using the sodium hydroxide solution. Weigh out approximately 1 gram of potassium hydrogen tartrate. transfer the solid into a clean, dry beaker. Add approximately 100 milliliters of distilled water to the beaker and stir the solution vigorously for 5 minutes with a glass stirring rod. Record the temperature of the solution. Filter the solution. Since the solution is saturated, it is essential that the filter paper, funnel, and collection beaker are dry prior to the filtration. Pour some of the filtrate, which is the filtered solution, into another dry beaker. This beaker is referred to as the secondary beaker.
So again, this is what's coming through the filter paper, right? In the first case, it is just the dissolved ions. There's going to be nothing on the bottom now. That is what's coming through our filtrate.
Prepare a 10 milliliter volumetric pipette as demonstrated in another video.
In ours, we are going to do 25 milliliters. We are going to pull 25 milliliters of that solution that has been filtered.
Measure 10 milliliters of the acid solution from the secondary beaker into a 250 milliliter Erlenmeyer flask.
Again, 25 milliliters we're considering 25 milliliters. Into the Erlenmeyer flask though, the cone top flask. And there we have our weak acid solution of hydrogen tartrate and potassium in there as well.
Add about 50 milliliters of distilled water, five to 8 drops of phenolphthalein. And then titrate with the standard sodium hydroxide solution to the end point.
So there's a waste container. She's going to take the air bubbles out at the bottom and flick it with her finger, get all the air bubbles out. And measures the starting point to 2 decimal places. This is our initial volume that you'll see in the lab, the initial volume.
The solution will be a faint pink when the endpoint is reached.
Now, at the end point, we know that our hydroxide ion concentrations have knocked out, if you will, all of our hydrogens. I should say take.
Record the volume of sodium
hydrogen
hydroxide used in the titration.
This will be our final volume reading, so we know how much.
Record the concentrations of the 4 potassium nitrate solutions. Used as a solvent. 100 milliliters of a potassium nitrate solution will be used as a solvent.
Okay, so the first one was deionized water, just like what we are going to do. The next one they use potassium nitrate. We are using potassium chloride. So this right here then already has a common ion in it. 0.1 molarity potassium chloride in our case.
Weigh out approximately 1 gram of potassium hydrogen tartrate and transfer the solid into a clean, dry beaker.
And then the same thing, we're going to filter this.
Record the temperature of the solution. Repeat the procedure with the remaining 3 solutions of potassium nitrate as the solvent. To be more efficient, while one partner is titrating, the other partner should be preparing another saturated solution of potassium hydrogen tartrate. Clean the glassware and put away the equipment.
Okay, so now these again are my 3 solutions that have been filtered. Okay, we're going to do this with just deionized water. Then for this one, we have the common ion. And here, this is my common ion, K+. Here's my original common ion that came for the potassium hydrogen tartrate. And we have Cl-. Again, we're calling these Cl- then inert ions. We're trying to keep them the same. And then in this one, in our control group, to keep our ion strength the same as a control group, we're using sodium chloride. And we're going to titrate till it becomes a faint pink. And at the point it's a faint pink, we know that the hydrogens, the hydroxides here, have pulled all the hydrogens off at our end point. Okay? So, if you were doing the lab, you would do 2 25 milliliter samples of each one. And again, this is just our neutralization, where this hydrogen will be forced off by the hydroxide ion. Okay, so let's look at results. So I didn't do a new one. I'm using your exact lab that you have. And I'm trying to just clean this up a little bit to make it a little bit easier. So we're using 25 milliliters of potassium hydrogen tartrate. That has been filtered, right? So it is saturated. Saturated meaning no more will dissolve. This is our initial reading, and this is our final reading. So in this case, and I didn't do a second trial. I just kind of crossed it out. If we subtract these two out, it looks like we use 20.23 milliliters. Now, I am going to do one calculation here with you, and then I'm going to let you do the rest. Now, please don't skip the video, because at the end I've got some things written in here that you need. So, I like to do things on one line for conversions. I know some of you, I've watched some of you calculate, you don't do it that way, but bear with me here. Let's see if we can figure it out. We would do an average. This, of course, here would be the same if we had multiple trials here. So 20.23 milliliters. Now, remember, again, this is a 1-to-1 ratio. So I know that for my equation, I have hydrogen tartrate plus hydroxide ion, and this is going to give us water, of course, HOH, plus our tartrate 2- ion. Now, here's what we know. We know that this is 0.0500 molarity, and it took 20.23 milliliters, or 0.02023 liters. Right? So you know that we can get moles out of this. This is moles per liter times liters. So let's put this in one line. Now remember, it is a great solution technique in any science class. Start with the single unit number first, and then see if you can put the double unit number in there right away. That's how you do stuff in one row. So we have 0.0202 liters of solution. The concentration is 0.0500 mole of NaOH. I could put OH minus, but I guess I can put NaOH per liter of solution. So we know that liters of solution here are canceled out. I have moles of NaOH. It is a 1-to-1 ratio. I know some of you do this in one row, but now we know that there's 1 mole of NaOH. So 1 mole of hydrogen tartrate, HTar. Now, this is the moles of HTar, correct? That were in that saturated solution. And if you want molarity of HTar, my units here cancel out. If we want the molarity of this, how many liters of solution did we start with? Well, this doesn't have to look pretty as long as the units work out. Draw your line here. Put your liters down below. 25 milliliters, right? 0.02500 liters of solution. Isn't that molarity? That is the molarity of my HTar solution. And that molarity comes out to be 0.0405 molarity HTar. And we know that that is the same for K+. Right? There's no common ion in here. So I know my molarity here is 0.0405, 0.0405. So my Ksp here is going to be my concentration of K+, my concentration of HTar, which are exactly the same. So let's do 0.0405 squared, huh? So my Ksp is 0.00164. Well, how many grams? Let's do a solubility in grams per liter then. So if we do the solubility in grams per liter, this right here is moles per liter. So we can go 1 mole of Ktar, I put it up here, is 188.1 grams. And if you multiply this out, this is 7.62 grams. Now, That's only in water. So what do you think is going to happen to the solubility when we have the common ion potassium chloride? Now, this is a little bit mixed up. This is actually beaker 3 next. So the directions are a little bit mixed up from the order. So this is beaker 3. This is kind of our control beaker, if you will. So this is the number of milliliters. So there is no common ion here. So please go ahead and calculate this out. And get the grams per liter here. So what is your prediction? Do you think now, just using kind of this control group, you've got this, we want to have similar ion strength. We've got sodium chloride in there. Is the solubility up or down? And you can maybe already tell that by the numbers here. Okay, then we are going to beaker 2. But in beaker 2, we've got our common ion. And look at the numbers, drastically down. Drastically down. So make sure for your K plus ion here, they're not going to be the same. You can still figure out your molarity exactly the same, but you've got your common ion here, right? So make sure you take into account for your solution here, this common ion, that the potassium's already in there. Then we have some questions to do. And again, this is beaker number 2. Then we're going to complete these questions. And I know some of you do not have a printer. So what I did, in order to keep all the classes the same that are in Tao's lecture, we're doing everything exactly the same. So here is page 9. Okay. And I'm giving you exactly the same hints. And then you probably, again, you don't have a printer, let's save some paper. If you want to stop the YouTube video and just jot these down, then this will finish it off. You don't have to try to print this. And I don't know if you have a printer, to tell you the truth. Some of my students don't have printers. Hopefully it's COVID break here. Or you're out of ink, or you're out of paper or something. So I will just zoom this in as much as I can, stop the YouTube video, hit the pause, and then write these down and answer these. So then I need you to shoot an Adobe scan then of these 3. Please, please, please make sure they're legible, make sure they're all upright. Email it to yourself to double check. So if you do not watch the entire video, you won't even know this is on here. And I looked at the analytics on the last one. Not everybody watched the video, but I will text that out to you. Okay, so I will put this, I will have this all up. We are going to shoot then those last, what is it going to be, 3 pages, huh? So we're going to need pages 7, 8, and 9. Yeah. So you're going to submit pages 7, 8, and 9. Again, pause it right here, and then I am going to stop this video.